Today, I'll present our work AmpMap that can quantify amplification risk on the internet. Many recent high-impact DDoS attacks still continue to rely on amplification. These exploit many protocols such as Memcached, SSDP, and CLDAP, leading to 2.3 terabits per second attack. In an amplification attack, the attacker sends a spoofed UDP packet to a public-facing server, such as a DNS server. These requests are carefully crafted to elicit a server to respond with legitimate but large responses to the victim. Here, the size of the response is 50 times larger or has an amplification factor of 50. This factor can go as high as a few thousand, depending on a server and a protocol. For example, a possible amplification mode for DNS is setting the eDNS field to 0, record type to be any, while setting the maximum payload field to any value greater than 4,000. Despite many efforts, there are still many protocols and public-facing servers that can be exploited for these attacks. Given these continued threats, what we need is an amplification monitoring service. Given these many public-facing servers on the internet, such a service should identify what are the amplification mode and how much risk or amplification factor each mode induces. Having this service can enable many other use cases, such as informing capacity for provisioning defenses and informing protocol changes. Let's now look at some seemingly plausible solutions to build this service. First solution will count the number of protocol servers and scale by a constant factor from prior work. For example, the service says that the risk for DNS is 6 million servers times by a known risk factor of 28. Unfortunately, this solution assigns the same risk to all servers, which is grossly inaccurate. A slightly more advanced solution would find one or handful fixed modes and use them to probe each server. Unfortunately, the risk would still be very off, as it does not achieve coverage across many other modes. In fact, existing amplification analysis use these two techniques. A more extreme solution would send all possible protocol requests, which would DOS the server and hence infeasible. To summarize, the first two suffer from low accuracy and coverage, and then the last one has high overhead. These Strawman solutions highlight a fundamental tension in building a service that achieves high coverage across these modes with low overhead. The motivating question for our work is, can we achieve the best of both worlds and build such a service? Let us now understand the practical challenges of building this service. Consider building this service just for a single server for a single protocol. Even that is difficult. We need to consider and try a large input space of all protocol headers. Second, the amplification modes have complex structures, where some fields depend on each other, and then the search space is also non-contiguous. Extending this service for multiple servers also makes the problem even more difficult. As seen by different colors, servers have different configurations and data views. Hence, they have different modes, and we need to consider this dimension. Lastly, we need to repeat this process for multiple protocols with different protocol formats, and hence different modes. We present AmpMap, which is a low-footprint amplification monitoring service that overcomes these challenges. It takes a server IP list and protocol format as an input. Then it probes the servers in this list and outputs amplification mode and their risk for each server. The core idea is leveraging structural insight across packet header and server space to improve coverage with low overhead. Let's start with our insight to tackle a single server challenge. This large rectangle here represents the entire search space of protocol headers, and these small circles are the amplification mode we need to discover. For simplicity, let's assume that this protocol has 3 fields with specific values set, and these are the settings for different modes. What we observe is that across multiple protocols, that these modes overlap in field values as they share some of the similar settings. That is, to get from mode 1 to mode 2, we just need to change field 1 value from 0 to 2. To discover mode 3, we just need to change field 3 from mode 2. To discover mode 4, we just need to change field 3 from mode 1. However, to use this structure, we need to bootstrap one mode. We empirically find that random sampling is sufficient across multiple protocols. So to summarize, we achieve coverage across this mode by leveraging this locality structure. Let's briefly walk through how we tackle a multi-server challenge. Here's a search space for 2 distinct servers. Notice an overlap in some of the mode. In fact, we observe that while servers are not identical, they can share a subset of amplification modes as they implement the same protocol. We can leverage this property to reduce the overhead further by sharing insights across servers. Building on this and additional ones in the paper, we built AmpMap service, which runs in a distributed manner with one controller and n measurers. We scanned 10K servers each for 6 popular UDP-based protocols. AmpMap only incurs 48 kbps across 30 measurers to scan one protocol. AmpMap is general and extensible across UDP-based protocols and is also configurable by controlling the packet sending rate and horizontally scalable with the configurable number of measurers. Using AmpMap, we uncovered new amplification mode. Let's start with DNS. The known modes are any and text record types. This graph shows the percentage of vulnerable servers from our 10K server set, and then the amplification factor each server can induce across all record types. The highlighted ones here are the ones from prior work. For example, around 50% of the server can induce an amplification factor greater than 10 using text record type. Using AmpMap, we found that there are many other record types that can induce amplification factor greater than 10 for non-negligible percentage of server. Specifically, more than 20% of the servers can incur greater than 10 amplification factor using 19 other record types. Apart from DNS, we also uncovered new modes for other protocols. For NTP, the known mode is monlist, but we also found a number of other modes where in some cases the amplification factor can be greater than 500. For SNMP, the known mode is get bulk. However, we also find that get next can incur large amplification. For certain servers, the factor was higher than 200. To summarize, our findings imply that blocking these known modes alone is insufficient and leave other attack vectors for attackers. Our measurement also reveals significant diversity across servers and protocols. This box plot shows the distribution of maximum AF achievable by each server given a protocol. Let's look at NTP. The median AF is only 5, but the tail is very long and up to 1,300. Further, we also observe significant diversity across protocols. While the median is only 5 for NTP, it is greater than 200 for charging, with a very short tail, but Memcached has only a median of 1.7. This suggests that we cannot make simplifying assumptions and assign the same risk to all servers and protocols. One important implication of previous result is that prior techniques significantly misestimate the risk. Details are in the paper, but here is the TLDR version. For the known mode, prior work can under or overestimate the risk, such as 400 over approximation for NTP. Prior work would also miss significant risk imposed by this new mode. Please refer to the paper for more detail. To summarize, our findings imply that blocking or rate limiting one mode is highly insufficient. Hence, we need to consider new defenses. Also, our findings again confirm that to build an accurate monitoring service, we need to handle the diversity across servers, and you need a solution like AmpMap to achieve coverage across amplification modes. To conclude, DDoS attacks, amplification attacks, continue to cripple our internet. Unfortunately, we lack a systematic mechanism to precisely quantify the amplification risk. Hence, we built AmpMap, a low-footprint measurement system that can do that. AmpMap leverages structured insight to tackle the combinatorial explosion of input and server space. Our measurement uncovered new amplification mode across multiple protocols, also uncovers significant diversity in the risk across servers and protocols. We also demonstrated that using prior analysis can significantly misestimate the risk. Our findings imply the need for new defenses. For more detail, check out our website, code, and the paper. Thank you.